Okay, continue with this lecture. Last time we discussed up to Doppler bandwidth. After Doppler bandwidth, we have coherence time. So one is Doppler spread and one is coherence time. These two provide information about the time varying nature of the channel caused by the relative motion of base station and mobile or and movement of objects in the channel. So if you take an example of a mobile user can either be a person who is static or moving at a very low speed, or a mobile user can be in a fast moving vehicle. So different conditions, he can be static or moving at very low speed, or he is moving very fast. If he is in a car or in any other vehicle. So in that case, your coherence time will be short if a user is in a vehicle that is moving very fast. But if a user is not moving very fast, he is either static or moving very slow. In that case, coherence time can be large. So what is this coherence time? Coherence time is a time during which the channel condition or the channel state information remain same. Okay. So during this coherence time, the factors that may affect the communication will not vary. If a person is moving in a very fast moving vehicle, then coherence time will be very small, and every maybe in seconds, within the second, coherence time will be short as seconds, maybe less than second, maybe in microsecond, maybe in micro, or maybe in milliseconds. So these two provide that information, whereas Doppler spread can tell you that whether you are moving away or towards the base station. So there is a relative motion of the user with respect to base station, whether a user is moving away from the base station or moving toward the base station, that depend on the Doppler spread. If the frequency increases or decreases, based on that we can trail whether it is moving toward or away. So Doppler spread, that is B of D, is a measure of spectral broadening. So the first thing is Doppler spread. What is it? Is a measure of spectral broadening. मतलब कि ये spectral broadening की measure करता है whether it is in positive or in negative, caused by the time rate of change of mobile radio channel. A time rate of change of mobile radio channel means the change occur in a time. What is the rate of change? Means a mobile radio channel, whether it is changing too fast, then the time rate of change will be very small. If the mobile radio channel is not changing too fast, then the time rate of change will be very high. Means it will take like 5-6 seconds to change the mobile radio channel, whereas very low means in micro or milliseconds. So this Doppler spread basically depend on the coherence time, because the time rate of change of mobile radio channel is your coherence time. Range of frequencies over which received Doppler spectrum is non-zero. Means if a time rate of change on a mobile radio channel is changing, then Doppler spectrum will be a non-zero value. Means it will be either FC, that is the central frequency, minus f of d, that is the Doppler frequency, or it will be FC plus f of d. So for a single frequency sinusoidal signal, the received signal spectrum will consist of these two frequency components. As I mentioned, fc minus f of d or fc plus f of d. If the baseband signal bandwidth is much greater than the P of D, then the effects of Doppler spread are negligible. Means if you are adding 1 hertz or 2 hertz in 1000 hertz, or if you are adding 1 rupee or 2 rupee in 1000 rupees, then that is not a significant addition. Similarly, the effect of then Doppler spread is also negligible at the receiver if the baseband signal is much greater than the Doppler spread. And this is called slow fading. Slow fading channel means the channel is not changing too much. Slow fading is also directly related to the movement of the mobile station. Slow fading means user is not moving too fast. It is either static or it is moving very slowly. So in slow fading, the coherence time will also be on the higher side. So if coherence time is high, slow fading is there, then Doppler spreading is negligible. So there will be negligible effect of Doppler spread. So we will not worry about the Doppler spread in that case. So coherence time is the time, whereas the Doppler spread is in the frequency. So we can say that coherence time is the time domain dual of the Doppler spread. So if coherence time, so you can say they are like they have the inverse relation. If coherence time is too high, then Doppler spread will be negligible. If coherence time is very short, then Doppler spread will be significant. So that characterizes the time varying nature of frequency dispersiveness of channel in time domain. So means what changes will occur in frequency with respect to channel if there are certain changes in the time domain. So coherence time is given by approximately given by 1 over f of m. So that is an statistical measure of the time duration over which channel impulse response is essentially invariant. As I told you, this is the time during which channel will not change. So it is the time duration over which two received signals have a strong potential for amplitude correlation. A simple period of baseband signal is higher than TC. Received signal would have undergone distortion. मतलब के your symbol is not fitting into the coherence time. It is greater than the coherence time, then the received signal will have some distortion. If the time correlation function is above 0.5 for definition of TC, we get 1 over 16 pi f of m. We normally use TC is equal to 0.23 divided by f of m. If it is above 0.5 of the what was that term? A RMS delay spread, 0.5 RMS delay spread. So that 0.5 of the RMS is same as we did for the coherence bandwidth, as it is derived from the RMS delay spread. If coherence time again has the time correlation function above 0.5 for definition of TC, then we get TC is equal to 0.240423 divided by f of m. Then we have types of small scale fading. The type of fading experience depends on the relation between signal parameters, that is bandwidth, symbol period, etc, and channel parameters, RMS delay spread, and Doppler spread. So there are two parameters. One is the signal parameters, and other one is the channel parameters. Signal parameters include bandwidth and symbol period, and channel parameters include RMS delay spread and Doppler spread. Time dispersion and frequency dispersion mechanisms lead to four possible distinct effects. Multi-path delay spread leads to time dispersion and frequency selective fading, while Doppler spread leads to frequency dispersion and time selective fading. The two mechanisms are independent of each other. So one is time dispersion and one is frequency dispersion. Multi-path delay spread, delay due to the multiple signals, and multiple second signals can take multiple paths. So they can arrive at the receiver with delay, with multi-path delay. So that's we call as multi-path delay spread. So that will lead to time dispersion. Means one signal will be received at one time, other will receive at another time. So they will have the time dispersion, time discrepancies among them. So when we add them, there might be constructive addition or might be, but there will be in delay. So that delay may be variable delay. So that will lead to jitter. So anyway, that will be your time dispersion. And frequency selective fading. There will be some particular frequency where this fade will occur. Some particular frequency will hit. Whereas Doppler spread leads to frequency dispersion and time selective fading. Because during that time when frequency spread that caused to frequency dispersion, the signal may lose its strength when you have low coherence time, and the two mechanisms are independent. So small scale fading based on the frequency dispersion and time dispersion can be said as flat fading and frequency selective fading. So if the bandwidth of signal is less than bandwidth of channel and delay spread is less than symbol period, then we call that flat fading. And flat means it is same for all frequencies in the receive signal. Whatever that your signal is, every frequency will undergo this fade. Fade means reduction. There will be power reduction in all frequencies in that signal. Whereas frequency selective fading is not same for all frequencies. It happens when the bandwidth of signal is greater than the bandwidth of channel. So the bandwidth that is greater than the bandwidth of channel, that means the frequency components that cannot be fit in the channel bandwidth will be faded. And delay spread, if delay spread is greater than the symbol period, means one symbol is going into another symbol's time. That is means your delay spread is greater than the symbol period. Then you will have the frequency selective fade. In that case, different frequencies will undergo different fading. So that's why we call that frequency selective fading. Maybe some part of the frequency will be able to be received properly. Some frequency will not be. So that's why we call that frequency selective fading in that case. So this flat fading and frequency selective fading is based on the multi-path time delay spread. Means when signals are received in delay. And based on delay, what delay, how much delay, whether the delay is under the symbol period or whether the delay is greater than the symbol period. If it is greater than the symbol period, it is very not good because it will give you frequency selective fading. In other case, if one frequency component can be is receivable, so the others, because it is same for same for all frequency. So the first type flat fading is also good or bad. Good in the sense that if you can receive one frequency properly, you can receive all frequencies. Bad in a sense that it can either you can receive the whole signal or you can not receive the whole symbol. Either you receive the full symbol or you will receive no symbol. So it is 0 or 100. Whereas in frequency selective fading, it is like 20, 80, maybe whatever the percentage of frequencies hit. So in that case, you will only be looking for frequencies which are not receivable. Small scale fading based on Doppler spread has two types: fast fading and slow fading. In fast fading, we have high Doppler spread, means the user is moving in a very fast moving vehicle. Coherence time will be way less than the symbol period because the channel condition will be changing very rapidly when you move at a faster speed. So the channel variation will be faster than the baseband signal variation. Very true. That is called fast fading. Very dangerous. In fast fading, you may not be able to understand what is being transmitted from your side or what is transmitted from the other side. You will not be able to understand each other. In slow fading, low Doppler spread. Low Doppler spread means spread will be the bandwidth of the Doppler spread will be way less than the baseband signal bandwidth. And coherence time will be way greater than the symbol period. That means a symbol can be in one coherence time, can be transmitted, so there will be no dispersion. Channel variation slower than the baseband signal variations. So that means your signal can be transmitted very easily when we have slow fading. So flat fading channel characteristics. Distribution of instantaneous gain follow relay distribution. Channel induces amplitude which varies in time according to relay distribution. So in that case, radio channel has constant gain and linear phase response over bandwidth greater than the bandwidth of transmitted signal. Spectral characteristic of transmit signal preserved, but signal strength changes with time due to gain fluctuation caused by multipaths. Symbol period of transmitted signal is way greater than the multi-path delay spread of the channel, also known as amplitude varying channel or narrowband channel. Typical flat fading, deep fade minus require 20 to 30 dB more transmit power for low bit error rates. Same as for the frequency selective fading, their channel characteristics. So to overcome flat fading, we can increase the power simply to overcome flat fading. And its distribution can follow relay distribution. So you can model this small scale fading, particularly flat fading using relay distribution. And it is linear phase and constant gain response over bandwidth greater than bandwidth of transmitted signal. Whereas frequency selective fading channel characteristics are difficult to model. Rule of thumb is if symbol period is greater than chain of RMS delay spread, then we have flat fading. If it is less than train of the RMS delay spread, then it is frequency selective fading. In that case, radio channel has constant gain and linear phase response over bandwidth smaller than the bandwidth of transmitted signal. So previously we say that radio channel has constant gain and linear phase response over bandwidth greater than the transmitted signal bandwidth. Here it is smaller than bandwidth of transmitted signal. And the simple period of transmitted signal is less than multi-path delay spread of the channel. Means delay spread will be greater than the simple period of the transmit signal. So received signal includes multiple versions of the transmitted waveform attenuation and delayed distortion and ISI because your delay is greater than the simple period. So that means your simple period will be interrupting with the other symbols. So due to that, you might have the inter-symbol interference. Certain frequency component will have the greater gains and certain frequency component will have the lower gains. So that's why it's called frequency selective fading. Multiple delay approach or exceed symbol period. So this is a chart that shows you the coherence time and symbol period, Doppler bandwidth and the symbol period again. Transmit signals bandwidth, sorry. So matrix is illustrating type of fading explained by a signal as a function of symbol period baseband signal bandwidth. So it's self-explanatory. I move to another slide. So this is relay distribution used to describe the statistical time varying nature of received envelope of a flat signal of a flat fading signal or envelope of an individual multi-path component. So you can see the signal vary from 0 to 250 microseconds. So you see most of the time the signal levels are maintained at 5 dB. Most of the time you can see around 5 dB. Either except few instances where it dropped to minus 35 dB, but other than that, it is like 5 dB at 120 kilometer per hour. We use Gaussian distribution when there is a dominant stationary signal component, line of sight. Small scale fading in envelope distribution is Gaussian. Add a DC component to random multipassing. I told you that we have line of sight component and line of non-line of sight. Line of sight is that when mobile station and base station can communicate without any hindrance or any object. That means the in between user and base station, there is no object in between them. So that means a line of sight component present. If you cannot see a base station, means there are some obstacles in between you and the base station. Then in that case, we use the relay distribution when there is no line of sight component. Then we have BPSK over AWGN. So this is the actual transmitted signal 00101, and this is what we can get after the transmission. So it is still understandable that it is 00101 over relay channel. If you use the relay channel again, it is 00101, and this is bit rate for BPSK and WGN, and it is relay channel. So that's the conclusion of this lecture. After this, we have cellular concepts and fundamentals. So this one is an old report that says CAGR 2012 to 2017. So you can also find the latest one of 2023 or 2022, where you will can see the population and the growth of the cellular markets in different regions, and the increase in the data rate requirement or increase in the data. So all these reports show the strong increase in the data rate requirement in the future years or the forecasted years. So early history of cellular systems, the most successful wireless communication system is the cellular telephone system or mobile phone system. The convergence of radio and telephone began in 1915 when wireless voice transmission between New York and San Francisco was set up. In 1946, public mobile phone system service was introduced in 25 cities in the US. The early system used as a central transmitter covering a metropolitan area, inefficient use of spectrum, limited capacity. Example, only 542 users in New York. Then 1950, 1960, AT&T, Bell developed the cellular concept. The cellular concept exploits the signal power falls with distance. This means some set of frequencies can be reused at different locations. Then the original cellular system design was finalized in 1960. Regulatory delays caused deployment to occur in 1980s. The original technology adopted was out of date, and AT&T had abandoned cellular technology by then. Then the first analog cellular system, AMS, that is the Advanced Mobile Phone System, was developed in Chicago in 1983. The network was saturated by 1984. The FCC upped the bandwidth from 50 megahertz to 50 megahertz. More cities had set up cellular systems. There was an urgent need for digital cellular system, which increased capacity and better performance. So the second generation cellular system was digital that provide voicemail, and limited data communications, for example, SMS, email, web, etc. So these are the major 2G systems deemed digital. GSM in Europe, Asia, Australia, South American, US, some parts. IS 136 interim standard, North America, South America, Australia. Pacific Digital Cellular, Japan, DPDC. IS 95 again, interim standard 95 in North America, South Korea, Japan, China, South America, Australia. Major revolution, digital modulation and advanced DSP. So due to digital modulation and advanced DSP, 2G was launched in different parts of the world with different names and some different standards, but their object was to transmit data through digital modulation and advanced DSP. So in 1991, the first US digital cellular systems were installed in major US cities, known as, so that first standard known as Electronic Industry Association Standard IS 4454 and IS 135 allowed a gradual transition from the analog system. So how it is better than the ANS? It has 3 times more capacity. Pi by 4 differential QPSK, speech coding and TDMA were used. 3 users per 30 kilohertz compared to FM in AMS, whereas 30 kilohertz per user in FM AMS. Here we have 3 users per 3 kilohertz, so 3 times more capacity. And it was based on CDMA, was developed by Qualcomm and standardized as IS-95. So it was not TDMA, but the first this 1991 USDC was based on CDMA. And it uses 1.25 megahertz per channel and direct sequence spread spectrum, and it can operate at smaller signal to noise ratio, significant improvement in capacity compared to ANS. Then these are different other services, or the you can say the networks proposed in different years by different companies. So I just skip them. I also skip this slide. It's history. Then we have from 2G to 3G. 2G systems were designed mainly for voice communications, other applications, data modems with low bit rate, around 10 kilobits per second, and short messaging system, not suitable for advanced internet-based and multimedia streaming applications. There is a need for new generation mobile 3G. However, 2G system are widely deployed. An evolution path to 3G is needed to reduce cost, impact, and risk. So this is kind of evolution path from 2G to 3G. You can see from GSM, we go to GPRS, then to Edge to WCDMA, and then to HISPA. Uh, Whereas TDMA go like this, whereas CDMA go like CDMA 1, CDMA 2000, CDMA 2000, CDMA 2000, EVDV, WCDMA, and then to HISPA. So let's have a break of 5 minutes. We'll continue after the break. So different countries have different frequency spectrum for different applications. So this one you can see IMT 2000 uh, in Japan, Europe, and ITU is from like approximately 2100 megahertz to 2200 megahertz. Another IMT 2000 is from 1900 megahertz to 2000 megahertz. And in Europe, GSM 1800, Japan is also having 1900 to 2000 megahertz, whereas USA has different frequency spectrum. Convergence of technology and service. So one is technology convergence and another is service convergence, both combined to provide much better services for communication and multimedia. So technology convergence includes evolution into common digital platform for delivery of audio, visual content and application. And that may include audio, text, video, graphics, and data. Whereas the services to whom we can provide these services include PC, handphone, TV, digital, radio. Right. Where they are converting, it is 3G systems. A regulator needed to facilitate seamless evolution from separated market to convergence market. So the early radio mobile systems provide large coverage area with a single high power transmitter with an antenna mounted on a tall tower. Good coverage, but limited capacity due to limited frequency spectrum and no reuse of frequencies. So that is about the 1G because we have reuse of frequencies in 2G, GSM, and other 2G systems. Frequency spectrum is a limited resource, so regulators must ensure its efficient usage and consider many applications and interests. Initial system must be structured to achieve high capacity with a limited radio spectrum. So one fundamental limitation that we can see in providing high data rate to the users is the limitation of the spectrum. The spectrum that is again not unlimited resource, it's a limited resource, and much of the spectrum, or we can say all of the spectrum, that is, you can say a good spectrum for cellular communication has already been allocated. So if you want to increase the data rate, so you have to go with the innovation and the technology advancement, utilizing the same bandwidth and providing the high data rate. So the initial concept was that we say 1G concept or the AMS concept was similar to the FM radio concept, where we have a central transmitting station with an antenna providing coverage to a metropolitan city, good coverage but limited capacity. Then a concept of cellular communication was born, where we have a system level idea that calls for replacing a single high power transmitter, that is large cell, with many lower power transmitters, small cells, each providing coverage to a smaller portion of the service area. And each base station is allocated within a portion of all the channels available to the system. Neighboring base stations are assigned different groups of channels, so the interference between base stations and mobile users under their control is minimized. So here it is the concept of cellular communication. A network is divided into different cells, and the estimation of radio coverage of the cells, shape of the cells is practically it can be circular, but theoretically, for the calculation purpose, it is like hexagonal or honeycomb, you can say. Multiple carrier frequencies are deployed, different frequency in adjoining or neighboring cells. Cell size is vary from 100 meter to 35 kilometer, depending on user density, geography, transceiver power, etc. Hexagonal shape of cells is idealized. Cells overlap shapes depend on geography. If a user changes cells connection, hand over to the neighbor cell. Then we have frequency reuse. Cellular radio systems rely on intelligent allocation and reuse of channels throughout coverage region. Each cellular base station is allocated a group of radio channels to be used within a small geographical area called a cell. The base station's antennas are designed to achieve desired coverage with the particular cell. Frequency channels can be used to cover different cells, provided interference is within tolerable limits. The design and allocation process is called frequency reuse or frequency planning. So initially, when we deploy a cellular network, we do first have a first step of frequency planning, that how many cells should be in a cluster, what cluster size we should choose, uh, 3 cell cluster, 7 cell cluster, or uh, more than 7 cells in a cluster. So because when we have 3 cells only, so in that case, frequency reuse will be aggressive. In 7 cells, there will be non-aggressive frequency reuse. Uh, and the idea was that with the power and the distance, the power of the signal will drop with the covering of the distance, so that after that particular distance we can reuse the frequency. That is the idea behind frequency reuse. But even the reduction in power or the control over the power, you need to design a frequency planning in such a way that interference should be minimum. So consider a cellular system has a total of 8 duplex channels available for use. So if each cell is allocated a group of k channel, whereas k is less than s, and if the s channels are divided among n cells into unique and disjoint channel groups, which each have the same number of channels, the total number of available radio channels can be expressed as S is equal to K into N, where N cells which collectively use a complete set of available frequencies is called a cluster. So N is the number of cells in a cluster, K is the number of channels per cell, and S then SK will be equal to the total number of duplex channels. If a cluster is replicated for m times, then the capacity of the system will be equal to m of s, where s is equal to k of n, and c is the total capacity given by this expression, that is of the system. And the factor n is called cluster size and is typically equal to 4n or 12. The value of n is a function of how much interference a mobile or base station can tolerate while maintaining a sufficient quality of communications. Small n is desirable to maximize capacity. The frequency reuse factor is given by 1 over n. Hexagonal geometry has exactly 6 equidistant neighbors. The lines joining the centers of any cell, and each of its neighbors are separated by multiples of 60 degrees. Only certain cluster sizes and cell layout are possible. The number of cells per cluster n can only have values which satisfy this expression, that is I square plus ij plus j square. It means that you have to move I cells along any chain of hexagons and then turn 60 degrees counterclockwise and move j cells to find the next cell where you can reuse the same frequency. Like here, it is cluster 1, 2, 3, 4. So this is the first cluster you can see. So you move like I, then so this 7 will become like I square. So I should be 2 and j is equal to 1, that is 4. plus 1 plus 2, that is 7.
Excuse me, sir. On your mic, mute the other.
So we were here. I was saying that uh, this one is reused here. You can find this one by uh, counting I is equal to 2. That is from one center to this center. That is I is equal to 1. And from this center to this center, that is I is equal to 2. And J is equal to 1 by rotating to anti-clockwise 60 degrees. Similarly here, 1, 1, and 60 degrees. So you can find here. Similarly, this one. So this is how reuse works. We will have a separate lecture on frequency reuse, 60 degrees counterclockwise or clockwise, how to use that. we will see. Then this is the old concept. We have single base station coverage. We have a mobile stations and single base station is uh, and frequency shared by all mobile stations. And this frequency should be different to avoid the interference. Whereas the cellular architecture tells us that every base station will have a different set of frequencies, and these mobile stations can be using the same frequency if they are in the other cluster. So frequencies can be reused, but here frequencies cannot be reused. Frequency reuse scheme increases capacity and minimizes interference. Channel assignment strategy, fixed channel assignment, and dynamic channel assignment. In fixed channel assignment, each cell is allocated a predetermined set of voice channel, and any new call attempt can only be served by the unused channels. The call will be blocked if all channels in that cell are occupied. So that is your fixed channel assignment. So from the name, it is obvious that these number of channels are assigned, predetermined numbers are assigned before. Whereas dynamic channel assignment channels are not allocated to cells permanently. Allocate channels based on request, reduce the likelihood of blocking, increase capacity. So we don't predetermine the number of channels in dynamic channel assignment. Channels are available on demand or on the request from the base station. Then we have handoff strategies. Uh, I stop here. We will continue from handoff strategies in next class. That is an important topic. So need a fresh head. So if you have any question up to now, up to this point, you can ask.